is Ayhan. Günaydın will speak about expanding the ordered group of integers by Beatty sequences.
Thank you for the introduction. So now I'm gonna, oh yeah, I can share the screen.
Okay, great.
There you go. So, right, so this is my title. And before actually starting this, mathematical parts, I would like to say some things. First of all, I would like to ask native speakers how to pronounce this name. Actually, I used to call it Beatty sequences. And I watched some videos of the famous actor Warren Beatty to see how people pronounce it, and Americans apparently pronounce it as Beatty or something like that. I mean, this is my best approximation of that. But then I checked the actual mathematician person, and then I realized something that I haven't known before. He was the dean of the mathematics faculty at the University of Toronto. So in that respect, this title is very appropriate. Right. And I also want to make a remark about Fields Institute. I mean, as Chris noted, a lot of us here were there in 2009, and it was really very precious time for me. I mean, for my mathematical development mostly. So I'm very sad that we cannot be there now. Anyway, so one final remark. Some parts of this work is joined with my student, Melissa. Well, so I'm going to talk about expansions of this structure. And the joint part with Melissa is the expansions of this part. Okay, and mostly I'm going to talk about this actually, expansions of the integers without the order. And at some point, I'm gonna tell you what I realized. I realized that all these results can be extended to the ordering after a little observation. Okay. All right, so, and also you will see it is kind of related to some things that Chris said, and I'll make a remark when we come there. So we just fix an irrational. Okay. Bigger than 1, and this will be fixed until the end of the talk. And at the end, I'll say something about, like, if it is a quadratic number or something else, we have some extra properties, but at the moment, it's just an irrational, so we don't have much properties. So I'll introduce 2 sequences. So as the promised Beatty sequences. So Beatty sequence generated by R is, I'll show it like this. So the terms are floor of NR, okay, for positive N. So, I mean, since R is bigger than 1, no term repeats, and it's an increasing sequence. There's no repetition and so on. And a related sequence is, well, people call this term word of slope R. So this is another sequence actually. So its terms are these. Okay. So the difference between the floors of n plus 1 over R and NR. And again, since R is bigger than 1, this number is either 0 or 1. Right? So that's why people call this a word. So this is a word in the alphabet 0, 1. Okay. And actually, okay, I want to add one word here. This is the characteristic Sturmian word. It's not important for this talk, so I'll just refer to it as the Sturmian word. Okay, so we have these two sequences, and the first one is just an increasing sequence of integers, and the second one is a word of infinite words of alphabet 0, 1. But there is a relation between them. Oh, sorry, before that. So PR, okay, PR plus is just the set of terms of the Beatty sequence. And when I write PR, it is and is among all the integers, but not 0. There's this funny little technical detail that you have to take out 0. Okay. And by using the properties of the floor function, actually, this is just the positive ones and the negative ones are these. Okay, so just knowing PR plus, you know PR. Okay, so our aim is to study this structure. Okay, and as I say, actually, I'll most of the times talk about this, and towards the end, I'll say, okay, ordering is fine as well. Okay, so first some observations. So first of all, for any integer, okay, let me write this as m. Okay, m being in PR is the same as s sub m being 1. Okay, so what's s sub m? Sorry, I forgot to write. This is s sub m. Okay, and well, I mean, here I just defined it for natural numbers, but sorry, this is s sub n. Okay. So there's this funny thing. There's this m. Yeah, okay. So we have this. So you know a very concrete relation between these two sequences. Okay, so something is in the Beatty sequence if and only if when you go and look at Sm here, it is 1. Okay, so in a lot of ways, I mean, expanding by PR or this infinite word is the same thing. Okay, let me give a little proof of this just to give you the taste of this. So if m is what was it? So kr for some k. Okay. So this means that m is between, okay, so kr drops down to m. And if you go one more step, you went too far. So this is if and only if this. Now dividing by r, you get k minus 1 over r is between r. Okay, so from here, you see that the floor of m over r is actually k minus 1. And you can also see that plus 1 over r falls here, which is this. So you see that the floor of this is just k. So their difference is 1. Okay, which is exactly s m in this case. Okay, so right. So I mean, for instance, if r is between 1 and 2, so this sequence increases by 1 or 2, right? So this SR somehow codes when it increases by 2, okay, something like that. Anyway, so we have this equality. We have this. Now, what does this mean? Let's observe that. So S sub n equals 1. I'll just write down the definition. So, and I want to write floor as this. So you take out the sorry, what's this part called? I forgot. Right. So it is this. Okay. So how can this happen? How can this number be 1? So this one cancels out this one, right? So we have something like 1 over r minus, so what is this number? This number is this minus 0 or 1, okay? So these are canceled out as well. Oh, sorry, I said something wrong. I have plus 1 over r minus 0 or 1. Okay? So this number here is the sum of these two things. Okay, and you either take out nothing or take out 1. So when you take out 1 is that if this number is bigger than 1, right? And how can that happen? I mean, this is exactly what we want. And how can this be bigger? So this happens, so let's write the end result. So this just means this number here is bigger than 1. Or we have this. Okay, so, and also remember, we know that this equals n being in the predicate. Okay. So we have this, and this is really the key observation. Why? Because if you don't realize this, and then you try to work with this subset of integers, it's very funny. I mean, it looks like there is some order, and then if you go further enough, that order doesn't happen anymore. Okay, so it's very say upsetting when you work with that. But when you do this observation, you can put everything in the circle, right? So this means that if you just look at, I mean, if you don't care about the integer part and only care about this, then that number should be here. So PR, not PR, but the part of that fractional part is in PR. Okay? Sorry, is in this interval. So the elements of PR are exactly the numbers n, so that the fractional part of this falls in here. Okay, so we start to look at, so it's a good idea to work modulo 1. So what we do is we carry everything into the circle. So this is my notation for this talk of the circle. So this is unit circle in C. And we have the exponential map. And I don't want to care much about this 2 pi I part. So I have this, okay? This is the usual map. Now, to use that observation, I define another map from Z into S. So I send a natural number to E of n over that number, okay? So, I mean, you can think this as, first you go to 1 over RZ in reals, then you apply E, okay? All right, so now this, the image of this, I'll call it as gamma R, is a subset of S, okay? It's a multiplicative subset of S. And this is exactly what Chris was calling m mu, m omega. So my omega is R, and this is exactly the multiplicative group generated by E of 1 over R, which is exactly x 2 pi I divided by R. Okay? So this is the cyclic subgroup of the circle generated by that number. Okay? So in that respect, we have this connection with Chris's talk, but I mean, it's not exactly the same thing because we are expanding integers by something. Okay, now, I mean, we don't have multiplication at all. We just work with this. I mean, okay, we have the multiplication here, of course, but in the original structure, we only care about the additive integers. Okay. Okay, so
I had a
yes.
little question. So is this set gamma R dense in the circle or not?
It is, yeah.
It is, okay.
I mean, okay, yeah. Thank you for this question. So I forgot to say, I mean, all the infinite subgroups of S are dense actually.
Right.
And this
right.
is very important.
Yeah, okay, thank you.
So, yeah, you're welcome. So, okay, it is dense in S. So now that we mentioned that, the topology of S is given by intervals. Well, I'll call them orientation intervals. Okay, so what are these things? So take two elements, write them like this, distinct elements. So, and choose A and B in a way that their difference is between 0 and 1. I mean, I'm not claiming B and A are in between 0 and 1, but then just their difference, okay? So if you have this, so the orientation interval determined by alpha and beta is all the gammas such that gamma is E of C for some C between A and B. Okay, so it's nothing really. So you take this alpha, you take this beta, and then this is this interval. But I mean, the funny thing is beta alpha is also an interval, right? I mean, which is what's different than the usual ordering. So if you go other way around, it's also an interval. All right. I mean, in this picture, if okay, so here's one. If one is not in between them, like this, you can choose A and B to be between 0 and 1, of course. Anyway, so the topology of S is given by this. So it seems like we have this Euclidean kind of topology around. So of course we have, but then this will help us. Why did I say that? Because by this observation above, okay, so look at this. So this is, if you apply E to this, okay, let me write it somewhere else. Okay, so we have this. Now take the E of this, and E doesn't see the integer part, so these are like this. So this one should be bigger than this. But the question is, what's this? So this just means that, okay, so this just means that E of an R is here. Okay, in this interval. So let me mark it here. So note that this actually is nothing but just h of n. So this is 1. This is this number. So this is exactly where age maps. So age of PR maps in this interval. Okay. So, I mean, we haven't done anything really. I mean, we just, sorry. So this observation means this, and then we just like made a circle out of this picture. So the structure that we care about, for the moment, I'm not going to put the ordering. So this structure is isomorphic via H to this. Now, group operation is multiplication, and I'll still call it PR. So what is this PR? This is this interval. Oh, sorry, this is, I'm sorry, this is E. But if you look closely, this is actually age of -1. Okay. Because I mean, this number is just R minus 1 over R, which is exactly age of -1. So this interval, but of course, gamma points, okay? Gamma are points. So this picture is just the circle, but of course, gamma R is just a dense subset of it. So we take it as a cyclic abelian group, and then we expand it by this interval. Okay. Now, okay, let me go back here. When I introduced this, these intervals, let me introduce another thing. So O, alpha, beta, gamma are elements of the circle. This means, okay, it's a definition. Beta is in the interval alpha, gamma. Okay, so we have this ternary relation on the circle, which I used to call orientation in my thesis, but there are a lot of other names, okay? So some people call it cyclic ordering, I think, and so on. There are a lot of names and a lot of names for this concept, and a lot of people working on it. So I'm not going to try to list all of them. Right, so we have this orientation. So what we can do is consider gamma, okay, with orientation rather than putting this interval, okay? So this is an interval in gamma. Instead, we can put all the orientations. So it looks like the thing that we want to work with is a reduct of this, but it's not actually a reduct. So this is interdefinable with this. So why? I mean, if you have one interval, you have all the other intervals, right? So for instance, okay, so this interval is of length age of 1. So if you want to construct another interval of smaller length, you just shift PR as much as you want and then intersect. Okay, so I hope this is clear what I'm trying to explain. So if you want to construct, oops, an interval like this, and it is smaller than PR, so you put one copy of PR like this and another copy of PR like this. Of course, this is not PR, but some translates. Okay. And if you have a larger interval, okay, so in the ordered setting, you might have to put like arbitrarily many copies of PR next to each other to get arbitrarily large intervals. But here, all the intervals have finite length. I'm sorry, the finite multiple of PR, right? I mean, so you can only fit so many PRs in the full circle. So this is one advantage of like working in this compact setting. Okay. But yeah, so at the end, you can construct all the intervals, hence the full Ternary relation of orientation. Okay, so we could as well work in here. Any questions so far?
Let me see.
Okay.
So if you yeah. But but okay, maybe
So do you have doubts about this interdefinability?
no, but I'm trying to remember now. Can if you are in the original interval 8 minus 1 to 1 and and you have and you want to say that you have a point, 2 points there, the first point and the second point, and you want to say that the first point is earlier than the second point. How do you say that?
Okay, so
in terms of this predicate for
so,
PR.
Right, so you want to say O1 alpha beta, for instance.
Yeah, right.
So you want to say this. So how do you say this? This is the same as saying maybe it's best to write this like this. So I shift everything. So this means that 1 is between alpha inverse and alpha inverse times beta. So
yeah,
so that's okay, right? So yeah. So what I do is so let's see. Right, so all I need is to construct this. So I want something like this. I mean, it's very hard to work in multiplicative notation. So
okay,
yeah, I want the picture to be this.
Right.
So what I do is I shift the predicate so that it is something like this. So it hits one of the endpoints.
Okay.
So, and then I shift it also like this, so that one of the endpoints is the other one.
Okay.
And then I say is one is in that. So in PR times something intersect PR times something else in terms of alpha and beta.
I see. Yeah, I guess I get. Yeah,
So
I guess
let
I
me
get
do
it.
once. So
Okay,
I think I just, yeah. So this, let me just say, I think it is this translate. Yeah. So I translate it by this, and then I translate it by the other one, and then I say one is in the intersection.
Okay, fine.
All right. So at this, I mean, is a quantifier free definable, right? I mean, so this is in a quantifier free way. So if I want to get anything like a quantifier nation or something, I could work in this one or in this one, it doesn't matter.
Okay.
So then I remembered my thesis in 2008. I went back and checked. I proved things like this. So I give some axiomatization, some 3 axioms saying what an orientation is. And I show that 2 regularly dense, whatever regularly dense means, this gamma R is, 2 regularly dense oriented abelian groups are are elementally equivalent if and only if their universal covers are. Okay, so we can define their universal covers. So you open it up, so you get a, I mean, if you want something like this, so gamma times z, but it's not the direct product. So the addition is a little bit different. So if you go, you add two elements, one of them is at this step, the other one is here. So you add them and you add the integer parts, you add the levels, but if they add up something bigger than one, you go one more level. Okay, so it's the universal cover, if you want, of gamma. So the point is, two oriented abelian groups are elementally equivalent if and only if their universal covers are, and their universal covers are oriented abelian groups, and we have a huge control on them. Okay, but I mean, this confused me a lot. Okay, so how this looks like, you take a Beatty sequence. Okay, you take two Beatty sequences, and then you consider these two oriented abelian groups. And of course, they come from the same group. They come from Z. So their universal cover is something like R. Okay, so how can, I mean, they're elementally equivalent. What's going on here? They shouldn't be elementally equivalent, right? I mean, different Beatty sequences should give different structures. So here's the catch. The thing is, we would like to work with this structure. We have to put one, okay? And when you send this to the other side, you get, so 0 is 1, 1 is age of 1, I'll call it eta, and still PR. Okay, so what I showed is this, and without this one, what I write comes a little bit late to you, I think. Okay, here it is. So without this one, I know the theory of this. Okay, the theory of this is determined by the universal cover of it. Okay, but when you have this one, things change a lot. Okay, you have a lot of arithmetic coming in because so this eta is some number here. Oh, sorry. So let's say eta is here. So this is inverse of eta. So this is PR. So then you start to ask questions like, okay, so this guy is not in the predicate. So is twice that guy or the square of this guy, is it in the predicate? Maybe it is, maybe not. Okay, maybe twice, I mean, age of 2 falls here. Okay, but then maybe 3 times here. So which ends fall in here? This again, I mean, goes back to determining what are the elements in the predicate. Okay, so this adding 1 gives us such a different structure. That's what I mean. Okay, so I mean, it's hard to determine the theory of this structure suddenly. Okay, so how much time do I have? Like 10 minutes or something?
I had, Jean-Philippe, I didn't get the results of your thesis you were referring to a minute ago. What was it exactly?
Because I said it very vaguely. So, okay, let me just do it correctly then. So you have an oriented abelian group like this, whatever it means, okay? Then you define, let's call it gamma star.
Yeah.
So it's a new group, but the multiplication here is a little bit different. So alpha comma m. Okay, I'll show it with additive notation, okay? So it is something like this. So alpha plus beta, m plus n. So it is like direct sum. If alpha and beta, how do we say this? It crosses 1. Okay, I don't know how to say this. Sorry, it doesn't cross 1. And it is something like this. plus 1 if you cross it.
Okay.
Sorry, what am I saying here?
Yeah. Okay.
So
Yeah.
then you can put an order on this. Okay, you can put an ordering on this. Now, here's the result. The theory of gamma plus with orientation is determined by theory of gamma star with this new addition and the ordering.
Okay. Okay.
Okay. So the ordering that you put, okay, so you think of gamma cross Z as a helix. So you just, it's like, you order it like you would.
Yeah.
Or,
Okay.
naturally. Okay. So, right. So the theory of this is determined by this. But when you add one constant, everything changes.
Okay. Okay. Thank you.
You're welcome. Thank you. Okay. So, how much time do I have, Victor? I kept lost.
Sorry, you have 15 minutes. Yeah.
15. Ah, very nice.
Yeah.
So now, how do we understand this? So the only way that I know is doing back and forth system. So let T be theory of just the group. Okay, and let's take two models of this. Okay, saturated enough. Okay, let's LF1 saturated. So take two substructures and isomorphism between them. Okay, so let's call this F. And then you take one element here. How can you extend this? How can you find the corresponding element on the other side? So if you're just working with the group, we know everything about this. I mean, after all, this is just theory of Z. Okay, so we know how to extend and so on. These are like ancient things. But what if we also have, okay, let's say L is with this expansion thing. How do I write this? So we consider these. Okay, so we just added these things. Of course, I mean, you just add them like that. I mean, there is no way that you can find the corresponding beta here. So how can we, I mean, what conditions we should put on these things, okay, so that we can extend such a map? I mean, assuming that such a map already respects P's, so it takes the part of P in A to the part of P in B, okay? Assuming that, how can we add some conditions so that we can extend this map to here? So the closest, I mean, the easiest thing that you should handle is things like this. Okay, so if you have an element like this, and if this element is in PR, then the element that you're gonna find should satisfy this. Okay, I'm not gonna say PR, just P. Okay, so we should at least have something like this. Of course, you should also take nth roots of these things, but I mean, that's the technical point. You can get rid of these roots. So all you have to handle, you can easily show that all you have to handle are things like this. Okay, so when maybe you can put A to the other side, of course, A is in A, of course. You can put A to the other side and just consider alpha to the M is in which translates by elements of A of P. Okay, this is the question that we have to answer. Then this one is solved by the following lemma. So this lemma happens in S actually. So let alpha, beta, gamma be in S and M some positive number, and alpha is less than beta in the sense of orientation, then gamma to the m is in alpha beta if and only if gamma is in, so you want to take the nth root of this interval, right? But it splits into m many pieces, so this is what happens. So you take alpha to the 1 over m, whatever it means, I'm not going to explain. So one of the roots. Okay. I mean, I make it as the smallest root. So this. Here, zeta m is the mth root of unity, primitive mth root of unity. So what happens is, so if you want to find out, okay, maybe I should make it a little bit bigger. Whose mth powers fall in here, okay? So this splits into m smaller pieces. The total length is the same actually, okay? So the length of this is 1/m of this, of the length of this. Okay? So it splits into m pieces. So let's go back. So if you want to understand such a thing, this means alpha to the m is in h minus 1a comma a, sorry, a inverse. And then, right, you can apply this lemma to this, but these elements are not in gamma. Okay, gamma has no torsion. I mean, gamma is Z as a group, so it has no torsion. So we don't have these elements. So you have to do something. Okay, so you have to somehow change this statement into a statement inside gamma. Okay, so this whole thing happens in S. So you have to take this fact and intersect everything with gamma. Of course, when you intersect with gamma, this thing is a finite union of convex sets, not intervals, but convex sets. But how do you know that it is definable actually? I mean, how do you, I mean, of course it is definable because of this, but how do you know that each piece is a definable thing? Okay, and they are, and then you can express it as a quantify free formula. So here's the fact following from this lemma. Given m, actually integer, sorry, m to the L, and I subset of this, okay, there is a quantify free L formula. Okay, so let me go back. L is this language. Sorry. I think to get quantify free, I need to put the other things too. Sorry, but it's not important really. Phi sub m I x y, so that in gamma, it is true that there exists a z, so that z to the m, sorry, how do I write this? Yeah, z to the mi is in xi, yi for I in I, and for everything else, it's not in there. This is a J also. Oh, sorry. If and only if phi m I x y. Okay. So I can express, I mean, I can get rid of this quantifier. Okay. So by using that lemma, I can get rid of this quantifier. So I get this quantifier free formula. So what happens is that by, let's go back here. So you want to find a similar beta here. So you want to check properties like this. So by saturation, you only have to check finite many of these things. So you take finite many A's, you take finite many M's. So on the other side, I mean, if there is one alpha here, which we know, it's a quantify free formula. So it holds in here. So it holds in here. So it holds in here. So there is such a beta. Okay, so we add this as an axiom. Okay, we add this as an axiom. Now, once you add this axiom, the back and forth system keeps going on. So it's a back and forth system. And do you need anything else? Well, the thing is, we haven't handled this situation of this constant eta yet. Okay, so we haven't handled the situation of this eta yet. And because of that, this back and forth thing might not even start. Okay, so this back and forth system will be a back and forth system, but it can be empty sometimes. So how do we guarantee that it's not empty? Okay, to guarantee that the back and forth system is not empty, we add the following axioms. So we add eta to the n is in PR if n is in PR, and eta to the n is not in PR if it is not. Okay, so such a trivial thing, but once you have this, the back and forth system is not empty. You can start from somewhere. So any two models are, you show that the theory is actually complete. Okay. Of course, I'm sweeping a lot of details under the rug, but this is what happens. So the axioms, let's go back. So it's very simple axiomatization, actually. So axioms of this, which we already know. Okay, so the axioms of this and this theory itself. These axioms capturing, getting rid of this quantifier. And we also add somehow, this is the type of eta somehow. Okay. Then, yes. Actually, we also prove the quantification results. So this actually determines the type. Anyway, so we get a complete theory. So this is all the work. This is what I did with Melissa. So how do you extend to if you add the ordering? So what happens is when you find this beta, you found it among things like this, right? We found this in this set. This set is either finite, either empty. If it is not empty, it's a finite union of convex sets. So if you have a dense subset, okay, dense subset like the positive elements, I'm gonna write it down in a bit, but let me show it on this picture first. So if you have a dense subset, then if this set is not empty, you have a member of that dense set in there. So what I mean is that if you consider age of natural numbers, okay, which is a subset of gamma r, of course, is dense. And adding ordering is the same as adding natural numbers as a predicate, okay, in quotation marks. So if you want to check that alpha satisfies a certain cut over this A, all you have to do is find it in that convex set and satisfying the cut also. And then satisfying the cut is a dense set. So because of that, extending to the ordering comes almost for free. Okay, there's of course things to check. This is the first remark, and I'll finish with one last remark. We did this work last year, sometime around, exactly 1 year ago. I gave a talk, and then Philip Hieronymi asked, so how about decidability? Can you tell us from your experimentation whether this theory is when it is decidable? Because we know that it's not decidable in some cases. Okay, we know that it's decidable if R is a quadratic number. This is, I think, a result of Philip with some other people. I'm sorry about this. I should have written this somewhere. And there are some R's for which the theory is not decidable. So when is it decidable? So the axioms. So this part, of course, is decidable. I mean, it's a computable set of axioms. So is this. I mean, one has to check that. But these axioms, I wanted to write them down, but they're fairly simple. And then you can even write down the Turing machine computing these axioms. So this one is under control as well. So they're computable. And this one, even though they are so simple, I mean, this happens if and only if, okay, this is a conjecture, but I think it's 80% true. This set of axioms is computable if and only if eta itself, sorry, not eta, R itself is a computable number. Okay, so one has to check these details, but I'm almost sure. Okay, so this is the result about decidability. And on that remark, I'll stop. Thank you.
Thank you.
Okay. Yeah. Questions?
Excuse me. Can I ask something?